Okay, thank you for waiting and thank you for introducing. I'm happy to be here to present GradualReality, a system that enhances physical object interaction in virtual reality via interaction state-aware blending. My name is Hyuna So. I'm a PhD student at Seoul National University, and this work is done by a great collaboration with Juhan Lee, Professors Rajesh Balan and Young-Kil Lee. Personally, when I'm exhausted and need to refresh myself from research, I'd like to escape to a quiet campsite. But if I ran off to a campsite every single time I got tired, my PhD would probably take over 20 years. So luckily, as an alternative, I can immerse myself into the virtual campsite by wearing VR headset without leaving my office. But what I truly want to do isn't just to see the scenery statically. To continuously enjoy this unique virtual experience, we need ongoing interaction with our daily physical objects, such as taking a sip of coffee from a physical cup or working on my physical devices, while still highly immersed into the virtual campsite. Cross-reality offers such interactions that occurs between virtual environment and physical world. To enable it, we need to bring the physical objects, such as this cup, into the virtual environment. But merging the vastly different two worlds into one seamless experience is very challenging. For this experience, the design goals can be summarized in threefold. First, a high level of presence in the virtual reality should be maintained, while simultaneously providing sufficient usability for interacting with physical objects. Since cross-reality involves constant movement between virtual and physical worlds, gradual transitions are also essential for preserving both presence and usability. We designed GradualReality to achieve these goals. This novel cross-reality system dynamically adjusts the blending of virtual and physical worlds based on the context of the user's interaction. This approach is grounded on our insight that as interaction with the physical object progresses, the type of required physical world information changes. GradualReality exposes the exact amount of physical information required for the current interaction context in the virtual environment to maximize presence while simultaneously ensuring usability. Let's take a look at how prior works have supported cross-reality interactions. They have explored how to blend the physical objects into the virtual environment, and virtual proxy replaces physical objects with virtual counterparts that share similar characteristics, such as size and shape. For example, this bottle can be rendered as a virtual flashlight. When these virtual objects are aligned with a theme of virtual environment, such as these drawers into a virtual sci-fi panel, it can offer a high level of presence. However, since the virtual object doesn't convey all the characteristics of the physical object, even simpler interactions such as grabbing it accurately or opening the bottle can be difficult. On the other hand, pass-through overlays a physical world view on top of the virtual environment, allowing precise interactions like typing on a keyboard or pouring water exactly. However, it causes a significant degradation in the presence as too much real-world information is exposed. So we can observe that existing blending methods inherently involve a trade-off between presence and usability. But they rigidly applied only a single blending method to all different types of physical object interactions, resulting in a limitation to fully achieve the cross-reality design goals. To overcome these limitations, we designed interaction state-aware blending approach. Moving away from solely relying on a single blending method, our key contribution is utilizing multiple blending methods aligning with the user's natural flow of physical object interaction, thereby facilitating fine-grained transition between virtual and physical worlds. To realize this, we categorize the user's physical object interaction context into 4 states: perceive, approach, avoid, and manipulate. For each state, it employs the most optimal blending methods: virtual proxy, affordance control, boundary box, and pass-through to provide the best balance between presence and usability. The key idea of state classification is based on our observation that as interaction progresses, users gradually need more information about the physical world. Specifically, in perceived state, the existence of physical object is recognized. So simple information such as location and type is enough. Next, in approach state, the user reaches out to grasp the object accurately, understanding where to grab. In manipulate state, physical objects are used according to user's own intention. And for further fine-grained transition, we introduce two complexity levels here. Simple manipulate for less intricate physical object handling that occurs in the object basic shape and where it is grabbed. Complex manipulate involves the deformation in the object, so the exact appearance is required. For more precise tracking of interaction state, we classify the object into two types, interaction target and non-target objects. So non-target objects remain in passive state as they are not actively engaged in the interaction. But when the target object moves close to the non-target object, they transition to the avoid state for safe navigation, requiring boundary information. These progressive transitions between states follow the intuitive flow of physical object interaction, thus ensuring natural cross-related experience. We then design blending methods tailored to each interaction state that convey different types and levels of physical object information. The key considerations were optimizing presence while simultaneously providing the exact level of physical world awareness needed to ensure usability for each state. Let's take a look how it works through a video. Here, the user is relaxing in a virtual campsite while interacting with a mug, mini drawers, container, and a water jug. Initially, in passive state, we use virtual proxy that mirrors the primitive shape, size, and function of the physical object, such as this container, into the virtual wooden box. It integrates physical objects into virtual environment and aids user awareness of their existence. We transition to approach and simple manipulate state as user moves toward the container. Here, affordance contour is employed to highlight interactable areas such as the handle of container. When the user moves the grabbed target object, boundary box outline the nearby non-target objects such as the drawers and jug here, moving them to avoid the state. We chose to use affordance contour to cover most interactions in the manipulate state, thereby moving away from solely relying on pass-through and maximizing presence. The affordance contour highlights parts like handles and knobs for secure grabbing, as well as simple manipulable areas such as cover and jug and lid. Lastly, for dynamically changing objects in complex manipulate state, pass-through is manually triggered. It enables precise perception for tasks such as pouring water to the exact level. With the interaction state-aware blending approach, we implemented a fully working system, GradualReality. Please refer to my paper for more details about the system implementation. To show the generalizability of the system, we applied GradualReality to 5 different scenarios. And here, I'll show you a VR gym scenario. Let's imagine a user who is deeply engaged in a virtual dungeon game, and he wants to make his boring workout more exciting by doing it in a dungeon. GradualReality can bring physical barbells, weight plate, kettlebell, and bottle into the virtual dungeon for this user. He can fully immerse into the virtual environment while loading the plate on the bar and lift to the barbell with ease and high usability. Users also can grab the kettlebell and detect the safe zone for swinging. After an intense workout, the user can rehydrate by drinking from the bottle over there, all without compromising presence and enjoying the user's favorite virtual space. We conducted a within subject study with 20 participants to evaluate the effectiveness of GradualReality. They performed tasks with daily objects while resting in a virtual campsite, including stacking objects, moving them without collisions, and pouring water, and then combining all these actions into one sequence. We compared 2 baselines and our GradualReality system. One is virtual proxy only, and another one is a combination of virtual proxy and pass-through. Based on our collected results, our system provides significantly improved presence than pass-through. Ours expenses lower workload compared to the both baselines and achieved 28% faster test completion time with 79 reduced task error. Please visit my poster for more insights and interesting observations. For our future research, we'd like to focus on several topics to discuss with you. First is applying gradual reality to practical real-world use cases. We are currently exploring how to recreate naval training in the submarines into the virtual reality while seamen stay in their houses and offices utilizing daily physical objects. We also can think about the two extreme cases of interaction state-aware blending. First, can we still design a single blending method that can perfectly cover both the immersion and presence? And on the other side, how much more fine-grained transition is required to maximize the benefit of our concept? Do we need like more than 10 states? Or would it be overwhelm the user in some point? Many interesting questions are here, and I look forward to discussing these ideas with you during the rest of the conference. The key takeaway from our research is that now we should move on to the new paradigm of utilizing multiple blending methods to support the detailed and optimal balance of presence and usability. Also, users' current interaction context should be considered to design the gradual transition in cross-reality. And this ends my talk, and I'm happy to take questions. Thank you.
Sure. Steve Feiner, Columbia University.
Hi.
So this looks really nice.
Thank you.
And however, it looks like there are a couple of places where you may, depending on what the person is doing, be needlessly exposing things that are changing, right? Like with that picture, for example, a big fat picture, I'm probably not going to try to pick it up with one hand because my hands are not big enough. So one thing I could do is reach out, and if I got really near that handle, I want to know the handle's there so I can pick it up. But if I reached out with two hands, right, maybe I don't need to see the handle unless the handle's going to get in the way. I can just pick it up the way that that picture appears to be in the virtual world and then pour it and then put it down again. So I was wondering if you were thinking about something about the hands of the user, the interaction parts of the user, and how they were posed to decide what to do.
You mean so the jog's handle is always rendered when the hand goes close, or?
So that's what I think you're doing now,
Yeah,
right?
that's
But
what
maybe
we
you
are
don't
doing.
need to do that if the user reaches out with two hands like this.
Oh, two hands.
They're probably not about to go and grab hold of a handle. They didn't even know it was there, and maybe
Okay.
you didn't need to tell them it was there.
All right, that's a great point. But actually, in the real world, we pour the water with one jug, one handle.
Depends if it's a big fat jug with no handle, I'll use two hands.
Okay, that can be possible with our approach still. But what I want to do was like enabling the real world interaction. So actually, we can, like in our scenario, we can utilize two hands for two other objects. And also you can grab the bottle as you told me that in two hands. So yeah, two hands interactions are also possible. Okay.
Hi, I'm Elodie Bousby from UPNA Lab in Spain. I was wondering, so from what I remember from annexing reality, it consisted as well in a framework where it would find the primitive of the object and then adjust the geometry and then map objects onto it, like virtual objects onto it. And so I was wondering how in your framework you map the objects together. Like, do you have like every time you're gonna see in the real life that it's a cylinder or something that's like, or that it's a teacup, you will map it directly, or like, do you have a whole set of objects, or how does it work?
Okay, that's a great question. So in our work currently, we manually map the virtual proxy to the physical object and attach the tracker for the tracking in real time. So actually, the important point in here was understanding the theme of virtual environment to provide a high presence to the user. So it is very difficult to automatically find the virtual object that can have similar shape, size, and affordance, but at the same time similar theme. So what we want to do is automatically generate the physical virtual object that can convey our design goals of the virtual proxy, but currently we are working on manually mapping the virtual objects. Thank you.
All right, let's thank our speaker, Juana.